Welcome to the Explainer. Today, we're going to take some pretty abstract mathematics and translate it into a really beautiful, logical, visual journey. We're unpacking the absolute foundational bedrock of calculus and advanced algebra, relations and functions. We're going to build this from the ground up, moving step by step through the exact rules that govern how numbers and sets interact with one another. Okay, let's kick things off with this quote from the renowned mathematician G.H. Hardy. He says, "There is no permanent place in the world for ugly mathematics." And he really hits the nail on the head here, reminding us that at its core, math isn't just about endlessly crunching numbers. It's about finding elegant, beautiful connections. Even if we can't always perfectly define mathematical beauty, we absolutely know it when we see the kind of perfectly logical relationships we're about to explore today. So here's our conceptual ladder for the day. We'll start with the meaning of relations, move into reflexive, symmetric, and transitive properties, check out the equivalence relation, explore functions as a special relation, dive into injective and surjective functions, and finally wrap up with finite versus infinite sets.
Let's jump right into Section 1, the meaning of relations.
Abstracting real-world connections into pure mathematics is a tradition championed by brilliant thinkers like Legendre Dirichlet, who you can see right here. Mathematically speaking, a relation from set A to set B is simply an arbitrary subset of their cross product. Now you might be wondering, why does this actually matter to us? Well, because this pure mathematical logic is literally the foundation of computer science, relational databases, and the algorithms that organize our entire digital world. We don't always need a recognizable real-world link. The pure mathematical rule is the glue that binds them. To really wrap our heads around relations, it helps to look at the two extreme examples. On the left, we've got the empty relation, where absolutely nothing connects. Think of a relation defining a sister in an all-boys school. Since there are obviously no sisters there, the set is completely empty. Then on the right, we have the universal relation, where absolutely everything connects. For example, if we define a relation as the difference in height between any two students is less than 3 meters, well, that applies to literally every single human student on Earth. Everything maps to everything. These are our two mathematical extremes. Moving on to Section 2, reflexive, symmetric, and transitive. First up is the reflexive relation. This simply means an object relates to itself. Every element A pairs with A. A perfect geometric example is a triangle. Every triangle is, of course, perfectly congruent to itself. It's a fundamental mirror image relationship. Next is the symmetric relation, which brilliantly illustrates a two-way street. If A relates to B, then B absolutely must relate to A. Think about perpendicular lines on a plane. If line 1 is perpendicular to line 2, the reverse is automatically, undeniably true. Line 2 is perpendicular to line 1. It just works flawlessly in both directions. Finally, we have transitive relations. This is where a chain reaction of connections links the very first item directly to the last. If A links to B and B links to C, then A inherently links to C. It's basically a stepping stone of logic that lets us connect distant data points through an intermediary.
All right, Section 3, the equivalence relation.
Collecting all three of these properties is kind of like hitting the mathematical trifecta, and it unlocks what we call an equivalence relation. If a relation manages to be reflexive, symmetric, and transitive all at the same time, it achieves a very special status. This trifecta allows mathematicians, and honestly computer programmers structuring massive databases, to partition sets into perfectly distinct, mutually disjoint subsets called equivalence classes. It essentially creates perfect, organized order out of vast sets of messy data. Now for Section 4, functions, a special relation. We're stepping up the ladder here, moving from basic relations to their much stricter, more structured siblings, functions. The crucial takeaway is that a function is still just a relation, but it comes with a much tighter set of rules. While relations can be kind of messy and map one input to multiple different outputs, a function demands absolute precision. Every single input from a domain must map to exactly one unambiguous output. No exceptions. This brings us to Section 5, injective and surjective functions. Let's unpack the formal jargon used to categorize these strict function rules. Translating the math here, injective, which is also called one-to-one, simply means that every single unique input gets its very own unique output. If the output of x1 equals the output of x2, well, it means the inputs x1 and x2 must have been the exact same thing to begin with. No two distinct inputs can ever share an output in an injective function. You can visually see the difference here. It contrasts a 1-1 function with a many-1 function, making that precise difference crystal clear. On the left, it's a perfect set of exclusive pathways. Every input gets its own private output. But on the right, we see a many-1 scenario, where multiple different inputs converge and share the exact same output. Both of these are technically functions, but only the one on the left is injective.
Next, we have the surjective function, commonly known as onto. This just means that no potential output gets left behind. Every single element in the destination set, the codomain, is hit by at least one input. The actual achieved outputs, which we call the range, perfectly equal the total possible outputs. Absolutely nothing is wasted.
And this brings us to the absolute pinnacle of function mapping, when a function manages to be both perfectly exclusive, meaning one-to-one, and leaves no output unused, meaning onto, at the exact same time it earns the ultimate title, bijective. It's a flawless pairing between two sets where every element has exactly one partner and literally no one is left out. Finally, Section 6, finite versus infinite sets. Things are about to get a little weird. I want you to look at this question and just think about it for a second, based on everything we've just covered. If a function is perfectly 1-1, meaning every input gets a unique output, does it mathematically guarantee that the function is also onto, meaning no outputs are left over? Well, the mind-bending answer is, it depends. For a finite, closed set of numbers, yes, absolutely. A 1-1 function within a finite set must be onto. There just isn't room for it not to be. But the moment we step into infinite sets, the rules completely break. For instance, if we take the infinite set of natural numbers and apply the function f of x equals 2x, every unique input gets a unique even output, right? So it's 1-1. But it is not onto, because all the odd numbers are completely skipped over, just left hanging out there in infinity. It leaves us with a pretty wild final thought. If the unbreakable rules of basic math bend so easily when stretched into infinity, what other mathematical certainties might fracture when pushed to their absolute limits?